Sorry for the delay. So today we're going to talk about different CNN architectures. So far, you learned about all the small building blocks that you can use to actually construct your CNN models, such as the convolutional layers, max pooling, fully connected layers, different activation functions, normalization layers. But now we'll talk about how to actually build a CNN from all those building blocks. And the task is not that easy because there are so many ways that you can connect all these parts together. And you also have to consider all the inner parameters, for example, the kernel size of the convolutional layer, like what is the window size of max pooling. So this is really a problem that people are trying to solve throughout the years. And today we're going to look at different architectures, starting from AlexNet and finishing with EfficientNet. And we're going to track their performance by evaluating them on a ImageNet visual recognition challenge. So this challenge, this challenge is a classification challenge. It consists of over 1 million training images, and there are 100,000 testing images for 1,000 class categories. So there's like a car, a dog, and so on. So the task in this challenge is to classify a given image into a specific category. Cool. So let's see how all the architectures performed and what were the tricks that the people used. So first of all, before the deep learning actually took off in this challenge, people were not using deep learning. They were using some handcrafted features or some expert decisions. So as you can see on this plot shows the top 5 error. So it means if the correct answer is in top 5 predictions of your model, you get 1 score. And if not, you get 0. So before 2012, so in 2011 and 2010, people were not using deep learning and they got error of 28% or something like that, which is pretty high. And in 2012, the first people to use the neural networks, deep neural networks in this challenge achieved an error of 16%, which dramatically improved over all the previous methods. And basically, some people say that the deep learning boom began since then. So this was a very important moment. Of course, the CNNs were around before, a very long time before this particular moment, but they were constrained to mostly smaller data sets or toy data sets. So people did not manage to train CNNs on such big data sets before. So people from AlexNet were the first to apply the CNN on this specific challenge. So let's see what is the architecture of AlexNet. And it actually resembles the modern architectures as well. So first of all, it starts with 5 convolutional layers. So the input is an image of size 224 by 224, a rectangular image with 3 channels. And then it's followed by 5 convolutional layers. Sometimes they're max pooling to reduce the resolution. And at the same time, they are also increasing the channel dimension in the middle. And after that, there are 3 fully connected layers that predict at the end the vector of probabilities, like the vector of size 1,000, which actually represents the, for a given image, what are the probabilities for each of the class labels from ImageNet dataset. So they used ReLU activation in comparison to previous CNNs that use 10H activation. They use max pooling, they applied dropouts, and they train it with stochastic gradient descent with momentum. One thing to note, why we have 2 branches here. So in 2012, the GPUs were relatively small compared to our days. So they had to actually split their model into 2 GPUs, which interacted only in some specific layers. So they passed this image to 2 GPUs, and then in some intermediate layers, they interconnected those channels. Do you have any question about this AlexNet architecture?
Who built this?
Huh?
Who built this?
Who built this? Alex Krzyzewski and Ilya Sutskever, probably heard this name from OpenAI, and Jeffrey Hinton. So yeah, this was a major moment. So after that, everybody tried to use deep neural networks and apply them to all the tasks. So this was the beginning of the kind of deep learning era. Cool. So for the next year, the network with the name ZFNet won, but we're not going to cover it deeply because it's just like some small hyperparameters tuning of the AlexNet, which additionally improved over the error that AlexNet achieved. And we'll go directly to the year 2014, and we're going to cover two architectures from there, the second place and the first place. So the second place was called VGG by Karen-Simonian and Zisserman. So again, the second place, but they have a very straightforward and elegant architecture, which is based on the following three rules. So the architecture is on the right, as you can see. First of all the convolutional layers have 3x3 kernels with stride 1 and padding 1. So basically, one such convolutional layer does not change the spatial dimension of an image. If the input is h by w, then when you apply the 3x3 convolution with padding 1 and stride 1, the output will also be of size h by w. All of their pooling layers are 2x2 with stride 2, so it's directly reducing the spatial dimensions by 2. And after pooling, they doubled the number of channels. So again, they went from a very spatially big but thin image, like with 3 channels. They decreased the spatial resolution and increased like the resolution channel-wise. The architecture is clear? Cool. So there was actually a reason to why they were using only 3x3 convolutional blocks instead of 5x5 or 11x11 kernel sizes, as it was done in AlexNet and ZFNet. So let's compare them to see what is the advantage of those blocks. First of all, let's calculate the receptive field. And maybe you can help me with this. First of all, can you tell me what's the receptive field of a 5x5 convolutional just block? What's the receptive field of just this block? 5x5. Exactly. And maybe you can also tell me what's the receptive field of the stack of 2 blocks of 3x3 convolutional layers, which is with padding 1.
9x9. Sorry.
5x5 also 5x5. Yes. So why? You can see, we can look at this image, and imagine that we start with a 5x5 image. We apply the convolutional layer with 3x3 kernel once. We get a 3x3 image, and then we apply it again, and we get 1x1 image. You can clearly see that the receptive field is 5x5 for those 2 convolutional layers. Is that clear? So this achieves the same receptive field as the 5x5 convolutional layer. So what about the parameters? Let's say the input channels is C and the output channels is also C. So can you tell me what's the parameter count for the 5x5 convolutional layer?
25C.
25C, and the output is also C channel, so it's 25C squared, right? Like you have C input channels and C output channels. And for the 3x3 stack of convolutional layers, it's 9C squared plus 9C squared, which is 18C squared. So
you have to put the additional one for the bias, no?
Not counting biases, just here. Just here's just for the counts themselves. Okay. So as you can see here, the number of parameters in this stack of 2 3x3 convolutional layers is less, which is nice. Given
C squared?
C is number of channels, so we have a input number of channels, let's say C, and the output is also C, so it preserves the number of channels. So the total number of parameters in this layer is C times the kernel size times the kernel size. So kernel size is 5 in this case, and so it's 25 times C squared. Not there?
I don't get why the C squared.
You have if you have just one convolutional like one filter, you are applied on the image of size like H times W times C, right? You have like a kernel of size like 5x5 by C, right? This is like the number of parameters, but you have C such filters to output C channels, right? So that's why it comes 25C times another C, 25C squared.
So the channels are fully connected in a sense?
No, this is like, again, this is convolutional block. This is not a fully connected layer.
No, but
I'm not sure.
the kernel, it is fully connected.
Each channel,
All the
kernel is by
yes.
the other channels before.
Thanks. We can also calculate the number of floating point operations. I'll do it for you because it's all approximate and not rigorous. So for a given input of size h by w, number of floating point operations is approximately 25c squared times hw, because you're applying your convolutional kernel on all the h times w input points. And for the stack of two convolutional layers with 3 by 3 kernels, it's 18c squared times h times w. So for the stack, you also need to perform less floating point operations. So like multiplications paired with an addition, which is also nice. So that's what they were aiming for. They tried to reduce the number of parameters and to reduce number of operations that you need to perform while keeping the same receptive field. That was the goal. And you can actually like stack more 3 by 3 convolutional channels. For example, stack of 3 will have the same receptive field as like a 7 by 7 convolutional filter, and will also have less parameters, which is nice. But of course, it comes with a price. And maybe you can guess. No, it's a memory. So for the memory, you'll have to use more memory for the 3 by 3 convolutional stack, because in the 5 by 5 convolutional layer, the memory will scale approximately as h times w times c. So the output of this 5 by 5 convolutional layer, you'll have to store it for backpropagation. It will be of approximately h times w times c, depending on the padding. And for the stack, you'll have to store both of their outputs. So it will be scaled approximately as 2 times h times w times c. So you'll have to spend more memory on this 3 by 3 convolutional stack compared to the 5 by 5 layer. Is it clear? Do you have questions?
No, why I understand the parametric multiple. The memory side is not clear. Why it's multiple by 3 only?
We're only counting now the memory required to store.
It's 25.
We need to. We're counting only the memory for the output, to store the output of this channel. So here, after the output of this 5 by 5 convolutional layer, your output will be like h times w times c, like depending on what padding you use, it could be like h minus 1, w minus 1 times c. But it will be approximately like this. And for the stack of 2 convolutional layers, you'll have to store twice as much, because you need to store the activations, like the output of both of those layers for backpropagation. Yes.
But we don't have to pay this cost then when we're in test time.
Yeah, in test time, yeah, that's true. But for training, you need to.
The amount of channels getting larger as we go through the network.
Yeah, usually like in these networks to train for classification, usually you decrease the spatial resolution, right? You decrease h and w as you go deeper. At the same time, you're increasing the channels, so like you're making the features more semantic, so like more meaningful. Like each feature now holds more information about the images.
So in this 64, 128, the channels are included there, right?
Yeah, this is the number of channels. And of course, after each convolutional layer, there is like an activation. It's not just stacking convolutional layers, there is also an activation function, like non-linearity in this, because otherwise it wouldn't make sense. Cool. So still there are some problems with this architecture. And if we'll now look at the graph of, yes.
Question about the intuition about the network, about the network. Why it's 2 convolution, and then 4 and 4? Any behind the empirical experiment? Is there any theoretical value?
I don't think there is a rigorous theoretical explanation to this. So they tried different versions of this VGG network. There was VGG16, VGG19, and I think it was just like all trying to find the better architecture, like more of an art. So yeah, as I said, there are some problems. First of all, like this is a plot that combines the memory usage, the number of operations, floating point operations used, and the parameter count, all in the same plot. And we can see that the initial layers, before we actually collapsed the spatial resolution, are consuming a lot of memory, because we also quickly increased the number of channels, but didn't apply the max pooling quickly enough. And you can see that at the end, like towards right, we have 3 fully connected layers which are actually taking a lot of parameters, because the fully connected layers are like matrices. They're very, very big, which are just like millions of parameters. You can see that the fully connected layer that is third from the end takes approximately like 100 million parameters, which is not great. You'll have to store all the gradients for this, and it will certainly slow your training. And so the next network, which actually won the competition for 2014, tried to avoid this. So the network is by Christian Sugedi and other people, and they introduced a GoogLeNet, and the error was 6.7. So we're actually approaching the human level of performance on this task, which is 5%. So on this specific task, the people perform as like they have an error of 5%. So let's look at their architecture, which is scary, but we'll go inside each of the components, and after that you'll see how modular it is, and we'll actually understand what's going on here. So in this architecture, they actually tried to avoid high memory usage in the beginning and the high parameter count at the end. So let's see how they did it for the beginning. So pretty simple. They just quickly reduced the spatial dimensions. So they applied the first convolutional layer was like a 7x7 with a stride of 2, yes, which quickly reduced the spatial dimensions, and they also applied max pooling just after that. So they kind of discarded a lot of spatial information in the image, which helped them reduce the memory consumption, which is nice. This is not an ideal solution because you will probably lose some information in the image, but it worked for them. And now, to reduce the parameter count at the end, they did the following. So the most parameters in this model come from the fully connected layers. So they decided we don't want fully connected layers. We'll do the following. So after they apply convolutions and pooling several times, their input was actually of size 7x7 by 1024. So pretty small. And after that, they just applied the average pooling with window size 7x7, which is basically a global average pooling, which results in a one vector of size 1024. And after that, a small fully connected layer to predict the classes themselves, like the 1,000 labels themselves. And that was their solution to reducing the parameter count, which is very nice. I think that was, since then, nobody used the fully connected layers at the end. Yes?
How do you even train a million parameters with 100 million parameters with 1.2 million images?
Yeah, so
I mean, I don't know. In physics, at least every time you have a free parameter, you need to do some experiment to edit.
so yeah, that's a very hard question that I'm not sure that I'll be able to answer, because like, why don't they overfit, right? Like, why doesn't the network memorize all the images? And the answer is the people I think are still trying to figure it out. There are some theoretical works on this, but I think this is out of scope for this tutorial. Maybe Shane has something to say about this, but okay. Yes.
Could you please repeat about the average pool points?
Average pooling? Yes. So towards the end of the network, like they reduced the spatial dimensions, right, by a lot. So at some point it became of size 7x7 by like 1024 channels. And then they just applied the average pooling. They pooled all the 7x7 like block into just one vector. So it became a 1x1 by 1024, which then you can kind of reshape to be just a vector of size 1024, and then apply a final fully connected layer and predict the classes. Yes.
In the first part of the network, they have 2 layers, I think, of 1x1 convolution, which is just a multiplication by a constant.
So 1x1.
One layer.
One line. Yeah. So 1x1 convolution can be just used to change the number of channels, right? So this is like, if you have an input of size h by w by c1, then you apply 1x1 convolution. It doesn't change the spatial dimensions of the image, but you can change the number of output channels. So I'm not sure exactly specifically what they did in this 1x1 convolution, but that's usually what the 1x1 convolution is used for, to just change the channel number. And actually, good point. We'll talk about this one-on-one convolution in a few minutes. Yes.
Why do you use the free softnut?
Softnut?
You can go back one picture.
Yeah, I'll talk about this in a minute. Okay. So now about the actually building block of GoogLeNet. They wanted to find a good building block that they can just stack one on top of another, and that will produce good results. So they came up with something that is called an Inception block. And they decided, like, we don't want to find a good kernel size. We just want to train them all. And so what they did, like, the naive implementation would be just given an input, apply 1 by 1, 3 by 3, and 5 by 5 convolution, and also apply a max pooling, and then stack them all channel-wise, and that will be your block. But there is a problem with this. Can you guess what's the problem?
Memory?
Memory, and then just basically computation complexity is just like too much to compute, because like there are too many channels. You end up with a lot of channels that you actually maybe don't want. So the same paper, they came up with an improvement on this, and this is an Inception block with a dimension reduction. So they used a 1 by 1 convolutions before this 3 by 3 and 5 by 5 convolution, and after the max pooling, to reduce the number of channels. So if the input was, let's say, of channels 256, then they apply 1 by 1 convolution to reduce the channels to 64, and only then apply the 3 by 3 convolution. So this allows them to greatly reduce the number of channels and does not sacrifice the error of the network. So after that, they just stacked these blocks one after another, and it worked for them. Any questions about this? Yes.
What about the filter concentration?
Filter, yeah, ignore just the filter, just concatenation. Ignore the word filter, just concatenate channel-wise, okay? Now, going to the question about why do we have 3 softmaxes. So, people already starting to notice that training big neural networks is hard. So something is going on there. So for some reason, the initial layers are not trained as well as the last layers. So hint, it's related to propagation of gradients. So we'll talk about them like in a few next slides. So to help actually train the initial layers of the network, they added some additional classification heads that they used only during training. So they just connected these classification heads to the intermediate channels of your network, and then applied this classification also there, and then propagated the gradients from those heads to the initial layers, which actually helped to boost the training of the initial layers. Nowadays, we don't do that because we know how to avoid the problems of vanishing gradients. And but that's the trick that they used, and this is just nice. You have questions? No. Okay. So next, as I said, people are trying to train more and more like a deeper network, but they were not succeeding when training like a network deeper than like 20 or 30 layers, which was a problem. And in 2015, the authors actually found a way to do that, found a way to train a very deep neural network, which consists of like hundreds of channels. And they won this challenge in 2015, and they actually surpassed the human performance on this task of classification. So this was the first neural network that was trained in a big scale with hundreds of channels, okay, tens of channels. And this is also a major moment in deep learning history. So first, their observation. So, and they noticed that when you train a like 20-layer neural network, it performs okay. And when you train the same way, the 56-layer neural network performs poorly. So they thought that it's odd because like 56-layer neural network should be like as capable as 20-layer neural network. So something is going on there. For example, if you just replace the remaining 36 layers with just like identity mappings that do nothing, it will be a 56-layer neural network, and it will perform as well as 20 layers. So it seems to be an optimization problem. So based on that, they tried to design their building block that will allow for optimization of very, very deep neural networks. So they introduced a residual block, a residual building block for neural networks. So this is a original building block, as we saw before, which is just like given an input x, you would transform it with like convolutional layers, and this is your output f of x. But what they wanted to actually encourage the network to use the identity mapping. So they did the following. So they just added the input x to the output of these convolutional channels. So the actual function will be not f of x, but f of x plus x. Another way how you can look at this is now, instead of trying to fit your neural network layers to predict the actual mapping from x to some other form, you're now predicting a residual to your x that you just add on top. So you have some x in some form, and you just want to find some deltas how to transform this x, like to steer it to. So now we will use the network layers to learn a residual mapping. Is this intuition clear? I will now explain why it actually helps for training deep neural networks. But if you have questions.
How do you solve there the difference in sizes?
So yeah, you have to keep the sizes the same, like this. So the x and f of x should have the same spatial size. So
it's like padding.
no, exactly the same. So like, for example, 2 3x3 convolutional layers with C channels as input and C channels as output, it will produce, and padding 1 and stride 1. It will produce exactly the same like size of the output at the end. Then you can just add element-wise x to the f of x. Cool.
I have another stupid question, but it's just I'm curious. When they do the challenge, are the humans also training on the million images, or just looking at the 1,000 images at the end?
You are saying how they evaluated human performance?
Yes.
I'm not sure that's human trained, but
it's concept that humans know, dogs and things like that, and they measure by humans annotated 12 million images, so they can check the agreement between human annotated. This gives you a rough estimate of what is
great. So let's see why it actually helps with training deeper neural networks. So here we have like a stack of those layers. If you just like stack one after another, you can see that since we have now this addition operation of like input to the output, the gradients will now flow through 2 branches. First branch is just like through the convolutional layers as before, but another branch is just directly to the input. So you calculate the gradient of the loss with respect to the input. One branch will pass through the convolutional layers. You'll multiply by the derivative of layers with respect to input, but another branch will be just multiplied by 1. So the derivative of loss with respect to this input, you'll just multiply by 1 to find the gradients of the x itself, which is just nice. If you just stack one after another, the gradients will not vanish, and like they will be allowed to freely like go from the end to the beginning, and kind of create a so-called gradient highway. So yeah, that's how we currently do this. Like since then, everybody's using skip connections to solve for vanishing gradients problem. This actually helps training a lot. That's what people do. Any questions on ResNet?
Can you explain again why that solves the problem of vanishing gradients?
So yeah, if you actually write down the like derivative of the output with respect to x, derivative of like f of x plus x with respect to x, you'll find out that like if you apply the chain rule from the end to the beginning, you'll see that maybe I should write down. No. The gradients like with respect to x will be just like derivative of loss with respect to f of x plus x times the derivative of f of x plus x with respect to x, and the derivative of f of x plus x with respect to x actually is just like derivative of f of x with respect to x plus 1. So this 1 is actually multiplying the gradients that come from the end, which allows to basically copy the gradients from the end to the beginning of this skip connection block. Is this clear? Yes, it is clear. Amazing. It's such a good. So yeah, what they did is just stack the these residual blocks one after another. So stack like without increasing number of channels, like 64 channels one after another. Then they applied the convolution with big strides to reduce the spatial dimensions twice as much, and then stacked these residual blocks again. This way you can scale this network like infinitely big. So don't do that, but they did. And actually they trained the 152-layer network, which won this challenge. So yeah, again, no fully connected layers at the end. They applied average pooling, this global average pooling, after they compressed the input well enough. And they also rapidly downsampled the input to reduce the memory consumption. Cool. So there are actually many more architectures that improved over ResNet. So we will not cover them in this tutorial, but just for you to be familiar with names, just I'll throw them at you, like DenseNet, ResNext, and squeeze and excitation networks try to improve the architecture and the accuracy of the ResNet since then. And there's also another line of work that tries to improve over the efficiency. So how to achieve the same accuracy with less resources, for example, to run on mobile devices or some less capable devices. So this is another line of work, which is very interesting. And actually, the last architecture that we'll cover today is somewhat in that sense of efficiency, but they posed a different question. Can we, given a fixed compute budget, so like a number of floating point operations, can we find an architecture that will give us the best accuracy? And yeah, they did it. They were able to train a network with hundreds of layers, and they found a way to scale the network very well. So they noticed the following. So usually we can expand our network in 3 different ways. First, we can increase the width, meaning increase the channel dimensions in each convolutional layer. We can increase the depth just by stacking more and more layers one after another. Or we can also increase the resolution of input images, which also is good, because when you work with high resolution images, you work with more information. But usually when people were expanding their network, they usually used like only one of those or 2 of those. And the authors wanted to find a method to how to expand the network like in a more profound, like in a better ways, how to scale the network globally. So for example, if you just increase the resolution of your input image, you also need to increase the depth, because you need to increase the receptive field of your network. Like if you don't, like your network will not see the entirety of the image. So you need to increase the depth. So that's why the authors try to find a better scaling method. And that's what they did. So how they did it? Given a fixed compute budget, let's say some floating point operations, let's say now we want to use 2 to the power of n more resources. 2 to the power of n more floating point operations are allowed now. Then we'll increase the depth. So like we'll have more layers multiplied by alpha to the power of n. The width, so the number of channels, is multiplied by beta to the power of n. And the resolution of an image is multiplied by gamma to the power of n, where alpha, beta, and gamma are scaling coefficients that are determined by a grid search on a very small model. So they start with some base architecture that they want to expand. They said, now let's say we have twice as many compute resources available. So n equals 1. So we have 2 to the power of 1 more resources available. And they did a grid search over alpha, beta, and gamma on how to scale this small model such that it will achieve a better accuracy. And they found, like just empirically, just like by this grid search, these coefficients of alpha, beta, and gamma, which they can apply later for scaling to much more resources. For example, now we have 4 times more of the resources, so n is equal to 2. Then you'll multiply your depth by alpha to the power of 2, beta to the power of 2, and gamma to the power of 2. So this actually allowed them to scale pretty well with this simple rule. Is this scaling scheme clear, or do I need to repeat this? Yes.
So if they're trying to determine the optimal way to distribute like the computation methods.
Yeah, like it's not in any way rigorous, like the best way to do that. But they said, okay, let's fix this simple rule that will just multiply the depth, the width, and the resolution by some constant when we scale it. And let's find this constants that we will apply for scaling. That's what they do. So, yeah, you can see on the top left side is there the curve of their models. On the x-axis, you have the floating point operations in billions, and on the y-axis, it's the accuracy of their models. And as you can see, they, for example, were able to find a model that consumes the same amount of like resources, that uses the same amount of floating point operations as ResNet 152, but actually achieves a much better accuracy. And on the other hand, they found a network that actually achieves the same accuracy as some ResNet network, but consumes much, much less resources. So their scaling operation allowed for like a deeper network that achieved better accuracy. Cool. Don't have any questions? That's nice. So this is the last architecture that we'll cover today, but that's not all. So let's sum up what we learned today. So you need to design your network according to task and resources, and you need to pay attention to parameters, floating point operations, and the memory size that you're using. So like how much memory your network is required to run on specific GPU. Use skip connections because they help to train your network. Usually you don't need to design your own architecture. In your projects, you probably will use some predetermined architecture from the people that actually do that for a living. So usually you just take some existing architecture and adapt, and like don't change it too much. And another point, very important, that will I want you to take from this tutorial is that usually you can use pre-trained models and adapt them to your specific task through transfer learning. So last few slides, we'll see what is a transfer learning. Let's say now you want to classify ultrasound images or X-ray images or do something with your MRI data. And so happens that you have on your hands a pretty nice classifier that was trained on another data, on let's say ImageNet, and it achieved very high accuracy. So you have an input as an image of a dog or something like that, and the output is probabilities for each class. So now if you just input the ultrasound image to your classifier, the output will be nonsense because there was no such labels in ImageNet and the probabilities won't make sense. But it turns out that the intermediate representations, so of this network, for example, if you look at like the last layer, like before actually the classification head, the representation of this image will be actually pretty good. So what you can do is you can replace the last classification head with your new linear layer, fix all the parameters before, and fine-tune your model on your data of ultrasound images just by fine-tuning this new classification layer at the end. So that way, you won't have to train your model from scratch. And this works because models like CNNs learn some general representations of an image. For example, like where are the edges? What are the differences of intensities in different parts of an image? So if you don't have a lot of data, you can't expect to train CNN on your data just from scratch because you'll have to train the CNNs like what are the edges and stuff like that. But the pre-existing, like already existing networks that were trained on some other data sets can be a good initial point. So you can use them in transfer learning. You don't have to just fix all the model layers before. You can also maybe unfreeze like the beginning of the network, like the input convolutional layer, if your input size is like not 3 channels as a regular image or 6 channels. So, but usually you don't train the entire network if you're just trying to apply this classifier from scratch.
Excuse me, can I ask a question?
Of course.
I understand why you want to freeze the convolutional layers, but why do you want to keep the first linear layer frozen? What does I mean? basically
Yeah.
it embeds it in a space that's completely different than the space the space you want, because these are not even, you know.
Yeah, you don't have to freeze like your linear layers. Maybe for this operation I should have like added my fixed image when I started the linear layers. But yes, you can just freeze the convolutional layers and train only the linear layers. But you can just start with fixing everything but the last layer. It depends on how much data you have. If you have like not that much data, you should freeze like most of your network. But if you have like a big data set, you can just continue training your network starting from this point without freezing anything. So it also depends on how much data you have.
Thank you so much.
So in practice, you can use all the models that we discussed today very easily just by loading them from a torch-based database. So just like from torch vision model import, and then the name of the model. And then there are also weights are coming with it. So for example, weights that were trained on ImageNet, you can easily load them or not if you want to start from a randomly initialized network. So yeah, that's how you do this in practice. Questions?
Has anybody done a search to see which of the models perform best as a base for training for the feature what was it called?
For learning?
Not for learning, for that for freezing the layers and then continuing for
Fine-tune.
transfer learning, sorry.
Yes. So I'm not aware of this, but I think a good rule of thumb just to start with the best model on some classification data set. Like if you want to classify something, and if you're working with images that are natural-ish or something like that, you need to start with like the model that achieves, for example, good accuracy on some data set. I don't have any works. I don't know any works that did like some rigorous search on this. So first one, in my experience before, I was even using like EfficientNet for transfer learning from like real images to spectrograms, and spectrograms are not even like images, natural images as you know them, but it still helped. Like when I started fine tuning from a pre-trained EfficientNet, it performed better on spectrograms on my specific task when compared to when I start from scratch. So, which is surprising.
Thank you.
Cool. So, thank you.